The rule of making the subshapes that we didn't have to worry about in the last example, but we do here, is that the subshape should be an easy to calculate shape for its, in this case, volume and centroid. But additionally, the shape, each shape should only be made of a single material. So we can't just take the entire rectangular solid because it's made of steel and brass. We still have to break it up into multiple shapes so that each one only has that single material to it. Right, so that's basically what it looks like. I'll put everything in meters for this problem. So how do we break this up into, or how can we break it up into subshapes? Again, so that every subshape only is made of one material. I'll start with B, is the piece that's made of brass. It's already a right triangular solid, so that's going to be an easy shape for us to work with. So I'm going to call this shape number 1. It's entirely made of brass, and it's a right triangular solid. So the stuff that's left, the stuff made of steel, is now a trapezoid, which again, we could treat as a single shape. I'm going to say break it down into even easier shapes. We can break that trapezoid into another right triangular solid and a rectangular solid. Both of them, though, made of steel. So I'm going to turn this into 3 shapes, 2 triangles, 1 rectangle. Solids, though. All right, so we have a larger table here that we have to worry about. We have 3 shapes we're working with. It's in 3D, so we're going to need the volume of each of these shapes. It's multiple materials, so we have to worry about the density of each shape. We're given the density in megagrams per cubic meter. We need to then calculate the mass of each shape, which will be in megagrams. We're in 3 dimensions, so we need the x tilde, we need the y tilde, and we're going to need a z tilde. These will be in meters. Then we're going to need an mx tilde, an my tilde, and then the mz tilde. So those are all the columns we're going to need to fill in for this problem. So let's start all the way on the left here. Shape number 1, how do we calculate the volume? 1/2 base times height times thickness we can use for the triangular solid. So 1/2 times 0.15 times 0.225 times 0.03. So for shape number 1, that volume will be 5.06 times 10 to the negative 4th cubic meters. Shape 2 actually has the same dimensions. It's also 0.15 at its base, 0.225 in its height, 0.03 in its thickness. So shape number 2 will have the same volume as shape number 1. And shape number 3 is a rectangular solid, so it will just be base times height times thickness. We don't divide by 2, so when we calculate that, it turns out to be 1.01 times 10 to the negative 3. Because we're looking for the center of mass, we're not going to add the total volume. We care about the total mass of the object. So this is where now we're going to account for the fact that it's made of, in this one, 2 different materials, but it could be more than 2. So shape number 1 is the brass, so we need to include the density of the brass. So that was the 8.74 megagrams per cubic meter, whereas 2 and 3 are both made of the steel, which is the 7.85. So in the problem, these values were given to us. In general, we could look them up in a material property table, which like in Unit 213, we're more likely to do that. So 1 and 2 have different densities, the same volume, and what that's going to mean is they have different masses, even though they're the same size and the same volume. So now the mass is what we want to calculate. It's going to be volume times density. So shape number 1 has a mass of 4.42 times 10 to the negative 3 megagrams. Shape 2 is lighter since it's less dense, 3.97 times 10 to the negative 3. And shape 3, 7.95 times 10 to the negative third megagrams. So we do want the total mass of the entire structure, 1.63 times 10 to the negative 2 megagrams. All right, so now we have to worry about, this goes back to just the geometry of each shape. Let's start with actually the easiest one. What's the y tilde of all three of our shapes going to be? Right, it'll be half of the thickness. So yeah, they all share the same thickness. So the centroid in the y direction will be half of that. So 0.015 for all three shapes. Yeah, if they had different thicknesses, then we would have to, there'll be more work involved in calculating this individually, but they all have the same thickness. Yeah. Oh, yes, you're correct. They are to the left side, so it's a negative 0.015. All right, now a little bit more work. We have to find the x tildes. We'll go to next. So for shape number 1, what will its x tilde be? Right, 250 millimeters or 0.25. So again, because it's a right triangle, from the right angle, we have to go a third of this distance is 0.05, which means this is 2/3 or 0.1, plus the 0.15. So we're left with 0.25 to go from the origin to the centroid of shape number 1 in the x direction. For shape number 2, its 1/3 is up here, so it's going to be the 0.05 plus the 0.15, so 0.2 for shape 2. And then shape 3 has a base of 0.15, but it's a rectangle, so half of that so 0.075 for shape 3. All of them are positive. They're all in the positive x direction. So in the z, same rule for shape number 1. It'll be now a third of its height, though. So a third of its height up in the z direction. So a third of 0.225 for the z tilde is going to give us, for shape number 1, 0.075 is a third of 0.225. For shape number 2, it's a third from its right angle. So it's actually going to be 2/3 of 0.225 for the location of its centroid. So 2/3 of 0.225, we get 0.15. Shape 3, half of its height now, so half of 0.225 will give us point to 3 digits, 0.113. Right, so again, hard part is done. We have to just be careful now because it's a center of mass problem. We're multiplying the mass by the x tilde, mass by y tilde, mass by z tilde. I'm not going to fill in all of these cells. You can do that on your own if you want. I'll just give you the summations of them for this. So the total of our mx tildes, 2.5 times 10 to the negative 3, negative 2.45 times 10 to the negative 4 in the my tildes, and 1.82 times 10 to the negative 3 for the mz tildes. So finally, we can calculate now the center of mass, which is not the same as the centroid for this problem, but the center of mass will be, in the x bar, it'll be the 2.5 times 10 to the negative 3, divided by, again, the total mass. So x, we get 0.15 meters. for y bar, negative 2.45 times 10 to the negative fourth over that same mass. Negative 0.015 meters, which we should have expected since they all have the same thickness. And taking the last value for z bar dividing by the total mass, we get z bar is 0.11 meters.